Hey guys, we're going to look at more integration by substitution. We've done integration by substitution before. These are just going to get a little bit more complex. So the idea is to get your integral into a form that is easier to take the antiderivative of. Obviously, we don't have a quotient rule. Oftentimes, whenever I see a quotient happening, I want to get it, if I can, into that 1 over u, so it can go back into our natural log. So typically what I'll try for my u is that denominator first. So in this case, my u would be sine of x plus 1. The derivative of u is going to be cosine of x dx. Now this already has those variables separated for us, and I like that because it can just go right in, and this is super convenient because it is also a substitute for this. So now my denominator is u. This whole thing right here is replaced by du. So you could put du on top, or you could just put your du out here and have a 1 on the top. I like to write it this way because it's way more obvious that it is that natural log. So now the antiderivative of 1 over u we know is ln u plus c, and then your job is to just put the u back in. So natural log of sine of x plus the 1, and then don't forget your plus c because we're doing an indefinite integral. Next one, again, I'm going to try the denominator first. So x squared plus 1, the derivative of that is 2x dx. Now, that's really close to the same thing that I want to get rid of up here, but it has this 2 right here. So an easy way to get rid of that is just to divide it over. So half du could replace that whole x dx over there. So I know that I could rewrite it as 1 over u times half du, but I don't need to have that half in there, so I could bring it out to the front and do 1 over u du like this. And then it's just the natural log again. So this is 1/2 times natural log of u. I'm going to go ahead and put the u back in there as x squared plus 1, and then add your plus c at the end. So sometimes we have to manipulate that to look like we want and replace the things that we want. Here, now we have a product of functions with a chain rule inside, so it gets a little bit messier. So it might not be as obvious what we want our u to be. Here, I'm going to go for my function inside of the function. That's going to be probably where it's going to be most helpful. So my u this time is going to be that cosine of x. If I take the derivative of that, you'll see we get negative sine of x dx, and that is almost these pieces right here. The only part that I have in there that I don't want is the negative. So again, we could divide by the negative or multiply both sides by negative, and we've got sine of x dx that we want to replace. So the negative, I'm going to go ahead and throw it in the front. The sine of x dx get replaced with that negative du. The negative I threw in the front. And then the e to the cosine, well, that is e to the power of u now. So everything's been replaced, and that is much easier to do the antiderivative of, because we know the antiderivative of e to the u is just e to the u. And then just put your u back in. So negative e to the cosine x, and then plus the c. Okay, I would like you to try d on your own. And then I would like you to try E on your own, and then I would like you to try F on your own. So take a second and look at those 3. Okay, now that you've tried those, check them, make sure you're good. Now, if you're good on those, I don't think you should have any problem with G and H. Go ahead and see if you can find the substitutes for G and H, and then we'll come back and check those in just a sec. Okay, so there are your G and your H. So this is just a little bit more complicated than the integration by substitution that we have done before. Now let's look at the next examples. Now these are going to get a little bit more complex as we go through them. So here we have the integral of x to the third times the square root of x squared plus 3. Again, I am going to go for the chain rule, the thing inside. So here my u is going to be x squared plus 3. And I would recommend writing small because some of these take up a little bit more space than I actually allowed for you. So take the derivative of this, and we've got our derivative of u equals 2x dx. Okay, so now I'm going to start trying to do some substitution and see what I've got left over, because hopefully you're seeing that this is not going to replace everything that I need. So I don't see a 2 in here that I'm going to need to replace, so I'm going to go ahead and divide. So I've got half of du is equal to x dx. Now the x is still helpful because I do have an x to the third dx, so I'm going to go ahead and look at that. So before I start substituting, I'm going to make this a little bit more obvious. So x times x squared is x to the third, and then we've got square root of x squared plus 3 dx. Now my x squared plus 3 is my u, so I can go ahead and say that this is u to the power of half, or you could leave it as square root, it doesn't matter. Here, I've got x dx, which could replace this x dx right here, and I need to replace it with half du. So I'm going to go ahead and put my du there, and I'm going to put my half over here. Now the problem is, I've taken care of this, I've taken care of my x dx with the half du, but now I am still left with that x squared. I cannot do an integral if I have multiple variables that are happening still. So I have to find another solution to get a replacement for x squared. So at this point, we go back up here, and I see x squared right here. If I manipulate this, I can say that x squared is the same thing as u minus 3. I have x squared in terms of u now. So now I have an actual replacement that could happen. So I have half the integral of my replacement for x squared, which is u minus 3, times my u to the power of half du. Now, I can actually distribute here. U to the power of half times u is u to the power of 3 halves. Add your exponents. U to the power of half times the negative 3, so negative 3 u to the power of half. And then I've got a very easy antiderivative to do here. Okay, so I just put my power rule in place, and I've got my add 1 and divide, add 1 and divide. So pause and finish that up, then sub your u back in. Okay, if you multiplied your fractions right and substituted your u back in, this is what we have here. So next up, I have b right here. I have x squared divided by x plus 2. Again, if I see a quotient, I am definitely going to try to get to my 1 over u. Now, it doesn't always work out, but most of the time, that's where I'm going to start. So I'm going to say my u is going to be x plus 2, which means the derivative of u is just the dx right there. Now, if I start to replace things, that means that I have my 1 over u, like I wanted. My dx is replaced with that du, but notice I still have this x squared that's hanging out over here. I don't want the x squared, so then we have to think, how can I get rid of that x squared? Because it didn't go away on its own. So we come back over here, and we say, okay, can I get x in terms of u? Well, I can, so x equals u minus 2. Except I don't want to replace x, I want to replace x squared. So if I square both sides, x squared is the same thing as u minus 2 all squared. Now, probably going to be a little nicer if I actually multiply that out, and then that is u squared minus 4u plus 4. I do that because if I put it in the numerator like it was, it'll probably look a little better. So let's go back to that form. So this x squared gets replaced with what we just did here. So u squared minus 4u plus 4 all divided by u du. Now, it's still a fraction, but notice that I could divide everything by u and create 3 separate terms, which means this is really the same as the integral of u when I divide it here, minus 4, and then 4 over u. I would really go ahead and say that that's 4 times u to the power of negative 1. And we know that this is a very easy integral to do. So you go ahead and pause and finish it up. Put your u back in where it goes. Okay, here you go. And actually, this last term that I put to a negative power would probably be easier if I did 4 times 1 over u, because that's that natural log that I ended up working with anyways. Okay, so there's your, oops, there's supposed to be a 4 there. I didn't write it in. 4 times natural log of x plus 2. So fix that. So hopefully that went okay for you. Go ahead and let's look at C. So here is an example of when, if I tried that denominator, it would end up with this chain rule that didn't end up working. So I'm going to give you a hint, and I'm going to say that your u, in this case, is going to be e to the power of x. When I do this, that means the derivative of u is just e to the power of x dx. Now, why does that help me? I can start replacing things with what I see. So I have a replacement. U is e to the x, right? So this top part right here is going to be replaced with a u over right here. E to the x squared is just e to the 2x. So I can say this is u squared plus the 4. And then my dx is not by itself right now. So I'm going to fix this by dividing by the e to the x. So 1 over e to the x du equals dx. So that means that dx needs to be replaced with my 1 over e to the x du. Now, hopefully some of you noticed that e to the x is just my u, so we can call that u. U in the denominator and u in the numerator actually simplify to just be 1. So now I am here to 1 over u squared plus 4 du. Now, that doesn't look like a simple antiderivative, but if you remember from 5.18, we had these formulas, and we have them on our formula book. And this middle one, the arctangent, looks very, very similar to what we have over here now, with my a squared being 4, which means my a is 2. And I can just follow the formula for arctangent, which is 1 over a, so 1 over 2 arctangent of x over a. Well, my x in this case is u, so I'm going to say u over 2 and then plus the c. Then just substitute your u back in, and we've got our end result. Okay, so for D, we're going to save that one, and then 4 and 5 we'll also do in class. So if you would like to try D, go for it. I would say hold on to 4 and 5.